Hello, my name is Michael. I come from old-fashioned. We are a Warsaw software house. We are Ruby programmers. We love to write nice-looking code, which I know some of you don't like for some reason. But at least we think it looks nice. But these days, Ruby isn't enough to write a whole full experience of interface for users. So we need to learn JavaScript to make the experience fluid on the front end for the users. And that's not all. Our needs are now going even higher than that. So we don't only need Ruby and JavaScript, we need more. Because our company builds even the smallest front-end websites and goes to bigger enterprise application. That's why we learn technologies all the time. We have hackathons. Every some time we have 2 days when we just hack and learn new stuff. You can go there with anyone from any team in the company. And we had an idea for an application during the hackathon that heavily used WebSockets. Because of that, because Rails handles it pretty badly, we decided to go for Phoenix. The hype for Phoenix was big at that time. And it was similar to Ruby because of the Elixir syntax and everything, so we decided to do it. And now we are also Elixir programmers. Because yeah, yeah, it was really easy to start an Elixir application in Phoenix to just implement the whole thing we wanted to do. So our application is called Sprint Poker IO, and I'll just give a quick demo of how it looks like. We can go to Sprint Poker IO. And here we go. We can add a new session, a demo session. I'll start this session. Hopefully it works. Yep, it works. But for the sake of the demo, I already have a session set up with 2 of my friends. I just gave them the link from the number, and now I can add some tickets because it's just a playing poker application. So I'll add some thematical tickets. Don't look at the rank of 5. Next. Don't fear my language. Fear my team. Just as the talks. And don't let the next rocket fall. Yeah, it's pretty important. Okay, so let's start voting. As you can see, don't look at the ring of fire. For me, it's pretty easy. I'll go with 2. Okay, voted. Now we can review points. I think it's pretty. It's harder, so we pick 13, and let's go to the next ticket. Don't fear my language. Yeah, that's easy. For me, it's easy. Okay, let's review the points. Yeah, it's easy. Okay, as you can see, it's automatically picked. Fear my team. Yep. Okay. They work with me. Yeah, so let's go with the 100. And yep. Oh, yep. I don't know what happened. Yeah, it's still a beta. But let's go. Okay. And the last ticket is don't let the next rocket fall. Yeah, it's hard. Okay, let's review the points. Okay, so let's go with 5. And something wrong happened. But anyway, usually it's pretty okay. So thank you, that's Sprint Poker. And the most important thing about it is, yep, it's open source, so we can go there. And thank you, that's all.
Okay, so my name is Sergey, and I suffer from not invented here syndrome. Mine is pretty bad. I wrote on my own database, but unfortunately it works very well, and it's
pretty stable. So it has a pretty good list of features. It uses Raft consensus algorithm. It uses SQLite as an SQL engine, and it uses LMTP as a storage engine. It supports the MySQL client-server protocol and also Thread, so you don't really need any special drivers. There is one for Erlang, that's just because we like a nice interface. It is horizontally scalable. So, what is ActiveDB actually? It's basically a database for software as a service apps. If you think about the list of these examples, all their database queries are user-specific. So if Gmail, for instance, you open your Gmail account, every database query that will be executed is only for you. So what emails I have has nothing to do with what emails some other user has. So if you wish to scale your database to a large number of users, a lot of companies like Dropbox sacrifice everything that makes a relational database good. You throw relations out the window, you have no joins, you have no foreign tables. They basically turn it into a key value store, which creates a lot of problems. So what ActiveDB does is well, Dropbox, theoretically, Gmail or Dropbox can shard their database down to a single user. So that is what ActiveDB is. It is a SQL database that is sharded by default. It works like this. It has many SQLite instances on top of a single LMTP file per node. And you can have any number of nodes. We use LMTP because you can't really run thousands of SQLite instances at the same time if they're all writing to disk in their own individual file. So we managed to integrate it with SQLite by throwing away the write-ahead long code. So when a write comes into SQLite, it generates a list of pages. We store those pages into LMDB. And because we have a very nice interface between the two, we can do stuff like compress every page. So all data is compressed. And usually compression ratio is like 30–50%, which means it's a pretty good payoff. You can't really scale Raft to, I don't know, 100 nodes, but you can, so this is why ActiveDB divides an ActiveDB setup into clusters. You have clusters of 1, 3, or 5 nodes, and Raft runs within that cluster. So when a request to write to an actor comes in from the client side, that name is hashed, which determines which cluster that actor must live in, so it sends that query to that cluster. And you can have any number of clusters. Because every actor or every SQLite instance is completely independent from any other. So it's very concurrent, much like Erlang. This is how a simple query looks like. So we added to SQL the first line, which is actor. We specify a type. You can have many different types, and every type has its own schema. Then you say name of the actor, and you have a list of flags, but right now we're only using create. This means that if the actor doesn't exist, create it. And we just insert a value. To perform a query, it's the same, my type, my actor, and select. You can also have multi-actor transactions. These are distributed ACID transactions. So if it fails on one actor, it will fail on all of them. And ActiveDB basically just reads the first line and sends off the rest of the SQL statements to every actor. In every distributed system, you have a problem with how to generate unique IDs. So this is ActiveDB provides this option. So when it receives this request, it will scan the string and replace any unique ID tag with a unique integer that is globally unique across the entire database. We also have key value store, which is basically a sharded table across all of your nodes. It has a user-defined schema, so you have multiple columns, you can have subtables. So it's a key value store which has incremental updates. So we can just, which many other key value stores only have overwrite the data. You can't have incremental updates. So it is very powerful and also performs very well. So that's it, thank you. It's open source, so check it out.
Hi guys, my name is Mirovic. I've been working with Erlang for a couple of years now, mostly for AOL platforms with Philip and Dennis, who gave a talk about our RDB system. Today I would like to show you the application for profiling for Erlang that I wrote recently to solve some of our performance problems. So why yet another profiling application? Well, I think that in the Erlang world we don't have a lot of tools for profiling. There is AvProf, there are other tools, but we find that they're not always the perfect tool for the job, and we often in our application the latency is very crucial for us. So if we have a bottleneck, we see on the graphs that some requests take longer than expected, and we always have we ask ourselves what is going on, why this request takes longer, and why we are wasting CPU. And usually it's because we have unoptimal code that is triggered by some very specific request, very specific data. So and also usually when we had such problems, we were writing custom code using DBG that was monitoring some functions and saving time measurements and then doing all this magic. For every case when we were trying to find bottleneck, we were writing the same stuff again. So I thought that it would be cool to have the tool that does it for you, uses DBG and has nice graphic interface. So I created an XProf. It's already on the GitHub. I will try to show you today how you could use it. So idea is simple. So basically, the idea is that you put XProf as a dependency to your project, and you basically type XProf start, and it starts the web server on your Erlang node. You can go to the website. Increase it a bit. So on the website, you can see that you have one button for turning on and off tracing, because sometimes tracing too much functions and functions that accept really large arguments can really slow down your system. So we really wanted this tool to be safe to use on a production. And here you have the function browser, which if you start typing, you can see the IntelliSense showing you all the functions that you can trace. This is using just information of all the loaded modules and does some tricks to get the information from it. So let's take a look at the short example.
Give me a small example.
Anyway, it's a very simple module, and basically the function that I want to see what is going on is calling timer sleep with a random value. So different calls to the expensive fun will take from 100 milliseconds to 1 second, right? So let's run this module. Okay, so now the Erlang VM is spawning a lot of processes that are executing this function. So every second, the expensive fun is called by different processes, and execution of this function takes from 100 milliseconds to 1 second. And what you can see in the graph here is that, first of all, there is a green line showing you how many times this function was called. The violet line here shows you what was the mean execution time, and all these red values show you the percentile values, percentile and percentiles. So this line here shows you what was the minimum execution time of expensive fun, and the top line, of course, shows you the max. And here is, for example, 75 percentile value showed. So you have all the information about the distribution of the execution time of that particular function. What is more, when we found out that some requests are taking long and we see a spike here, we would like to see what were the arguments to this function that's triggered in performance and make Erlang to execute this function for a long time. So here we can catch such function call. So here we give, for example, the value of what is the execution time above which we want to catch the arguments and the result from the function. So let's say that we want to see the arguments that were passed to the function that took more than 120 milliseconds, and we want to stop printing these functions in this web UI after catching 2 examples. So here you will see that we have these are 2 examples of this process. Executed this function. It took 130 milliseconds, and the arguments passed to this function was just a list with 132. Yeah, so that's basically it. You can find it on GitHub on my account.
Where is the web server running?
Web server is running in your Erlang application. So if you put it as a dependency and you start it, it starts the Cowboy web server.
So fprop is expensive to run, but running a website server on a running system is not expensive?
Well, if you run fprop, for example, you're tracing all the processes, for example, by default.
Take cprop or something. It's just that you're saying that it's expensive to run these things, but then you're running a web server that takes out resources from the system you're trying to performance
Are they on the same node?
Yes, we'll say no. I didn't see any actually impact on our system. We are using big machines, but I didn't see any footprint of this. The biggest footprint has tracing, and if you enable tracing on a function, for example, that is using accumulator, and you're getting and it's traversing a large list, then you'll see the big impact of Erlang VM copying all these arguments that were passed to each function call, and that has much more impact than running a Cowboy. So I found Cowboy very lightweight. And, okay.
Question?
Any more questions? Right, thank you.
I would like to talk about things that I wish I'd been told before I learned about the Ring of Fire. So let's talk about meshes. You already seen this picture already, yeah, we have some. In record we have some hash space where you hash the key, whatever it is. Then it's partitioned into some partitions, and the main point here is that partition is you have the constant amount of them. And it's the only, if you need to move data from one machine to another, it's the only the only unit of something that can be moved, with notable exception of reader size. And if you want to add replication, you just need to pick another partition. Then to actually run this somewhere, you need to assign those partitions to some nodes and spawn vnodes there. This is like ideal state of the cluster, and for each vnode we have some node that owns it, and this is called primaries. What happens when something goes wrong? Then we have first misconception that I thought for a long time that it would be handled by some other partition. That's not true. It will be handled by the same partition and by the same vnode, but it just will be executed on different node. So when primary goes back, we'll have some transition between actual state of the cluster and target state of the cluster. And for this time, those nodes will coexist. And yeah, handoff can happen in three different cases. Either you had a node going offline or network split, and then the cluster rejoined, and you got a fallback realizing that primary is there, or you change the target state of the cluster by adding more nodes, or you wanted to add to split your partitions and therefore trigger the resize. This is managed by Gossip subsystem. And this is well known, but what is less known, and actually another gotcha, is that React used to allow to manage the state of the ring by any node. But actually now it's only one pre-assigned node for each given ring that can actually modify the number of physical nodes in the cluster. And it's called time. And if you work with React Core, you probably work on all this. So let's talk about request. What's going on when you send the request? Okay, you have some API node, you have some coordinating point that gets information about who to talk to from ring manager or cache or whatever, and it sends that to vnode, right? No, there is a vnode proxy. Why it's there? First of all, it's for the reason of having like each index on each vnode, each possible index on each physical node. Because if you want to do this trick with fallbacks, then you probably want to be able to address everything, even if it's not yet there. And when request comes to the node that doesn't have a vnode for this index yet, it will be spawned by proxy. Another important thing that vnode proxy does is that it performs back pressure. It's this like big red thing. Let's assume it's a back pressure for this vnode. And actually when it happens, or when you have some failure, then you can end up in the situation when your vnode actually doesn't have some data that was written to your replicas during some failure. Then how can you get this data? Because if you end up with just this node responding to your reads, then you just won't get any data. How you can converge? You can use read repair, or you can use active anti-entropy. And here's another gotcha. Read repair maybe not what you want, because it means that for each read you probably will need to execute a write. And active anti-entropy, unless you use React KV, it's not there for you, at least in vanilla React Core. But there are hash trees. They are not documented widely, but if you look into this module, you will find documentation for them. Use them if you use React Core. And there is another goodie, it's cluster metadata. Basically, you have cluster-wide k-value storage for configuration. It's nice to have. And also you have coverage requests, so you can, also there, this is absolutely not documented as far as I know, but you can ask React Core to distribute your request efficiently across a set of nodes that covering your dataset. And also you can ask, not for just one key, but for the range of keys, and you can mix and match. And there are a lot way more things to use in React Core which are not documented, so you actually should read through the source. That's it.
Okay. Hi everybody. Just to quickly introduce myself, I'm a craftsman, mostly working over the web. Doing most of my work is open source. You can find on my GitHub Benoit C, and I'm working in Erlang, so another language that fit my needs. So today I will talk about Barrel, which was named Arcouch and started as a fork of CouchDB. But we decided since the beginning of the year to go a little further. And Barrel, this is a distributed database for the modern world. This is still a document-oriented database, which means we are storing documents in the database. The document is just a bunch of metadata that you store. They are mostly stored as JSON in Barrel, but also other serial things that can come later. Each document has a revision tree. We are keeping the history of the documents, mostly for consistency. So which means like in Wikipedia, when you want to update documents, you need to pass the revision you want to update. And if there is a conflict, you will get the conflicts back. Or you can force and store the conflicts with the documents. And when the document is replicated to another node, in both ways, it can be pull or push to the nodes. Then you have all the history of the document and make the decision about which conflicts you want to solve, which the revision is a good one, etc. etc. There is the original things with CouchDB and Barrel. There is a change feed, so each change you are able to get each change in the database and use the change feeds to replicate to another database, basically a log. You have views, CouchDB called that map and reduce, so you have possibilities to have a view on your data and pass a function on each document and index them incrementally. I mostly see that not as map reduce, but as a way to build virtual views over your DB and a way to shard depending on different parameters to build that bit. And this is very important in Barrel, like we just catch up. So over all the features that you can find in CouchDB, you have also the view change. So this is like the change feed on the database, but these are changed over the index, which is quite interesting. For example, if you want to build a virtual database, you are able to make a view, an index of your database, and get all the change, and then replicate this view of the database to another node or to another database. You have Bulkhead, which works with PouchDB and Couchbase Lite on mobile, which allows you to fetch multiple documents at the same time. Actually, the function has been imported in CouchDB recently. In Barrel, you have also revisited storage because it still suffers from some code from CouchDB and it's still slow, so some bits need to be replaced, and a lot have already been replaced in Barrel. But now we are revisiting the storage. There is a new replicator engine that we launched this week, and a new view engine to make things faster. There is an effort to maintain the CouchDB API, basically mostly for the replications, and a way to import back and forth from CouchDB to Barrel, from Barrel to CouchDB. But there won't be no Mongo-like query engines. Barrel is not a marketing effort. We don't want to be like in the other database. I think there are already a lot of databases that can reuse that, and the goal of Barrel is mostly to allow you to move your data very fast and very quickly next to your user. So Barrel is interested in location, data locations, and data movements. So we are more interested to find ways and to provide you the ways to put on match data that correspond to a device, to a user, or another database in another location. And Barrel is fully peer-to-peer. So the distribution of barrels that is coming is mostly chainable replication. So it means that you will be able to chain replication node by node in any way from different locations without any single proof of failure or even without any directions. So you will have contracts between nodes. And because data, I see data as Nils Stephenson defined that, data is not only a blob, this is also an application. An application is some data. And in KGB you have the couch apps on which I worked a lot. And in Barrel you have the replicated apps. So these are apps that came with the data that allows you to render them or transform them in the way you want. So I invite you to check on Barrel on barreldb.org. And voila, any help is welcome. Thank you.
Okay, that winds up for today. Thank you very much for coming. I hope you've enjoyed yourself. I have. I want to thank our sponsors again. So AOL especially, our platinum sponsor, us, and Basho, gold and silver as well for today. And for all of you for coming. I think we were over 100 people today, weren't we? Something like this. So it's been a very, very nice factory. Thank you. Well,